Lecture 5.2, the electromagnetic spectrum. One way of creating an electromagnetic wave is to oscillate an electric charge back and forth, which in turn radiates an electromagnetic wave. So a simple picture looks something like this. I have a positive charge. I could do the same for a negative charge. It's typically negative that actually occurs this way. And now I'm going to oscillate this up and down. In other words, I have an oscillating charge. And as a consequence, it radiates, it spontaneously emits, it radiates an electromagnetic wave. And it turns out that the frequency of oscillation, of course, oscillation of the charge is the frequency of the radiation. That is the electromagnetic radiation. So what I want to do here is I want to show you two videos. One of them is really terrible. I have a really good HTML file, but it uses Flash, but Flash is not supported anymore. So I'm going to show you one that's terrible and one that's better. Okay, so let me go to the first one. Here's the first one. This is the terrible one, but it actually gets the point across pretty well. So I have a central charge, and you can see the electric field. So now what happens? I'm going to start the video. And you can see that the charge is oscillating up and down, and as a consequence, it produces a wave, what looks like an electromagnetic wave. It just radiates off of that. Now, here's a second one. This is better, but not exactly what I wanted to show you here. So now check this one out. You can see that the charge is oscillating back and forth. And look at these circular waves leaving. That is an electromagnetic wave. So that's what I'm trying to show here when I say if I have an oscillating charge, it's going to do that. So what I'm going to say then that the frequency slash energy is the more important term of the oscillating charge will determine the type of electromagnetic radiation produced. So there's lots of images for electromagnetic spectrum, and here's one. I particularly like this one because it shows not only wavelength, which it shouldn't, but that's how we commonly describe it, and it shows it in terms of frequency, which is more realistic than wavelength, but it should be in terms of energy. And it turns out that there are really 6 variations of these electromagnetic radiations. Now, I'm going to separate these two. I shouldn't, but they're typically separated. One, there's radio waves, and a lot of times people will separate microwaves and radio waves. They're actually one and the same. Microwaves are on the higher end of the radio wave spectrum. This image doesn't show that, but that's what it really is. 3, then I have infrared. Then we have the tiny, tiny visible spectrum. Then we have ultraviolet. And then finally, 6 and 7 are X-rays and gamma rays. So the question is, why are these classifications? I would actually put gamma separate than X-rays, and then I would put UV all the way to radio waves in the same class. There's really 3 classes of electromagnetic waves, and it depends on how you produce them. But the way I'll show you here is that there's really only 3 ways to produce electromagnetic waves. So here we go. So then we want to ask the question, why is the electromagnetic spectrum broken up into classes? It depends on the energy scale of electrical interactions. I probably should have said electromagnetic interactions between, let's say, protons / neutrons in the nucleus and electron energy levels. So a good picture of the atom, unfortunately, I'm not going to do a good job of it, but the quantum picture of the atom has that electrons, as well as the nucleus, have what's called a shell structure or an energy level structure. So if I look at the nucleus actually has a shell structure or energy levels. And what that means here, so if I just look at just the electrons, we have these things called energy levels. Here I'll label them 1, 2, 3. Now note that this is not the quantum energy levels. This is actually the Bohr model energy levels, which are not great. Y is the electromagnetic spectrum broken up into classes. It depends on the energy scale of the electrical interaction between one protons slash neutrons in the nucleus and two electron energy levels. So I'm going to give you a rough quantum picture of what an atom looks like. The image that I'll show you is the Bohr model, which is not quantum mechanics. And what you'll see here is that I have energy levels. And down here, I have a nucleus that binds electrons to the nucleus. So let's say that here I'm showing you, let's say 4 energy levels, and electrons, they live where? They live in these shells. How they're there does not matter because that's not what we really care about. And these are electron energy levels. The quantum mechanical picture is more complicated. Along with this quantum mechanical picture here is that we know that these electrons are bound to this nucleus. We know that inside the nucleus, protons and neutrons are bound inside the nucleus by the strong force. So one can model the binding energy using potential wells. That trap, in this case, we'll say charged particles. Now note, a neutron is not charged, but it still has a potential well. So there's really only 2 ways that one can bind these guys here. So the highest binding energy have the deepest well. So if you look at this guy is going to be a deep well. And the deepest well are nuclear. Their nuclear wells are the deepest ones. And without going into units, the depth of these guys are around 10 million. So what's 10 million? 10 million really means 10 million electron volts. And in this case, what I'll say here is that in here, I'm going to have a positive charge. Now, if you look at this thing, this is the binding energy here. So the binding energy represents the potential energy, in this case, the electrical potential energy that keeps that proton inside the nucleus here. So then the other one here will range. And what you're going to see here is that if you look at now electron binding energies, you're going to have something that looks like this here. It turns out that they're considerably smaller. So now I'm going to look at electrons in this well. And the range of this varies quite a bit. They essentially vary from, so if I look at the depth of this guy, the depth is somewhere between, let's say, 10 to around 10,000 electron volts. So when you look at this binding energy, this is considerably smaller. So we're talking at least a factor of 1,000,000 times. So how hard is it to actually get some of these? Well, I mean, if you can get to 10 million electron volts, you can eject a proton out of the nucleus. If you get somewhere between 10 to 10,000 electron volts, you can eject electrons out of the atoms. So here's what we find here. So these guys, these are electron wells. And so here we go. So the deepest wells, okay, we could then say this here. So maybe I should write this instead of just saying it all the time. So here's what we find. The amount of energy required to remove a particle from a potential well. By the way, when I think about a potential well, I'm thinking that this right here represents the ground level, that this is at 0 right there, which I didn't say that before. So this is at 0. So they're stuck sort of like in the ground. So from a potential well depends on the depth. Of course they depend on the depth. Furthermore, this energy is proportional to frequency. And at lower energy level, at lower class levels, they typically write frequency as little f, but that's not the way it's typically written. It's written as the Greek letter nu. But this tells us here is that the energy is proportional to frequency, not wavelength, as I'll talk about here in a moment. So in other words, if I have a deeper well, that means then it requires higher energy to liberate or remove a particle, which then means that I have higher associated frequency. If I have a shallow well, then this is going to be a lower energy. You need a lower energy to remove the particle. So therefore, this is a lower frequency. Now, this is out of context, but I think it's worth really coming into it. that I'm going to say, note, in this discussion, I never mentioned wavelength. People have a tendency to talk about wavelength. That's not the core. I will talk about wavelength because that's the common way of talking about it. What you got to remember here is that it's the energy that is most important. Not the frequency or the wavelength when dealing with light. I'll talk about more on this later here, but here we go. So now we then say that the electromagnetic spectrum is really classified in terms of energy, but the most common way that people talk about the electromagnetic spectrum is wavelength. So I'm going to talk about this. I'll talk about this superficially about wavelength, but I'm always thinking energy. Okay? I'm always thinking energy. So here's the first one now. So the first one I want to look at is gamma rays. You know, I should be careful here. Let me come back up here because I realized I started to say something and I didn't finish saying it. So when you look at the deepest well has the highest energy light. And this belongs to gamma rays. So nuclear interactions produce the highest amount of energy. And no other process does that. So then when I look at electron wells, all of the other energies tell you, in other words, from X-rays to UV to visible, all the way to infrared to radio waves. Remember, I said microwaves are part of the radio wave spectrum. They're all produced by electronic wells. And that's why they have lower energy. But gamma rays have the highest energy because they're about 1,000,000 times deeper, the wells. So when I go and I talk about gamma rays, then we then say that they can only be produced by nuclear interactions. Of protons / neutrons jumping. Now, we didn't talk about jumping, but what we really mean by the word jumping, by the way, I should have put this, jumping from high to low energy levels. Now, you may have taken chemistry, and this is what you have here. And you may have heard about energy levels in chemistry, but if I look at the nucleus, so one of the images that you see a lot in the nucleus is something like this. And I'm just kind of randomly drawing a nucleus. So when I think about a nucleus, it has protons and it has neutrons here. So in other words, let's say that those reds here are my protons, the blues are my neutrons. And they have this binding energy that binds them all together. In other words, they have wells. So when I look at this well, it turns out that there are nuclear energy levels inside the nucleus. So when I go and I look at these guys, what you'll find here is that I typically see a double structure of where protons and neutrons live here. So as an example, maybe I have a proton structure like this, right? So these are my protons. And then I have a nucleus structure that may look, let's say, something like this here. And the one thing that you got to remember here is that this proton is then going to jump from a high energy to a low energy. So that means as it falls from here to here, that's a really big jump. How big of a jump is it? It's about 10 million electron volts. So that's a huge, huge jump compared to this guy. So as a consequence, you have to conserve energy. And so what happens here is that in this process, oops, I drew the arrow in the wrong direction. Here, let me get rid of that arrow here. There is an emission of a gamma ray. I'm drawing this too small. So when you're looking at this, this is what happens here. The depth of this binding energy, as I said before, this binding energy shows that if I start off with a huge binding energy, remember this is about 10 million electron volts, and then it jumps to a lower energy state, which is right here. So to conserve energy, oops, you know what? I should have made this color different. Let's say I make that green. Okay, so this is green here. And so what that means here is that this amount is the energy of the light, of the gamma ray. Oops. In other words, we then say that during the jump, during the jump, what did I say? During the jump, the proton radiates a gamma ray. That is about 10 million times stronger than visible light. So it's a big deal. You know, there's lots of ways to produce, you know, other types of rays, but when we talk about gamma rays, we only care about nuclear interactions. Let's go to the next one. So remember, everything after X-rays, everything's produced by electron changes. So now we have X-rays. So what do I know about X-rays? These guys are produced by ejecting inner electrons of atoms. And typically the way they do that is they do this with I think one of the first ones was a copper atom. Modern days, they typically use tungsten. But here's what we have here. Let me bring this up here. So for a copper atom, what do I have here? A copper atom, if you look at the structure, looks something like this here. Okay, look at this copper atom. And so for a copper atom, one knocks out a 1s electron. So what do I mean by that? So if I look at copper, you could see here, let's look at these numbers. Here's these numbers. So let's look at these numbers. And this is what this means here. So I have 1, 2, 3, 4. You can see that there are 4 numbers. So I have 1, 2, 3, 4. Now remember, this is not a good structure because I'm using the Bohr model, which is not very good. But that's what we have. And then here, which I'm not going to include anymore now, this guy is the nuclear charge. So when you look at this, look at the number here. It starts off with what? I start off with 2 electrons here, 18, 8, and then the one thing that I want you to pay attention, note that there's this 1 right here. So what does this mean? It means that on this shell, or this energy level, there's 2 electrons. In this one, they have 18, and then, oh, I reversed these. That is 18 up here. I know that that's a silly mistake. And then up here, there are 18 electrons. And then in the 4th shell, they have the 29th electron. This 29th electron is, very important in especially in circuits here, because that's how we get good conductors for electrons. So now what we're going to do here is that you're going to see one of these electrons, they're typically knocked out by an X-ray, they call it an X-ray tube. So when you knock it out, what actually happens? You then have the same structure, and guess what? I'm going to copy this. I should have copied it beforehand, but I'll modify it. I'm going to copy it, and I'm going to put it right here again. Remember, I'm not going to deal with the nucleus anymore. So now I've knocked out this electron right there. So what that means here is that now this guy is a hole. Because this is a hole, here's what happens. This electron jumps from here to there. And in this process, what does it do? It emits an X-ray. Okay. And why does it do that? Because this is high energy. Down here, this is a lower energy. So then if I look at the energy bar diagrams for this, here's what you're seeing here. So the gamma here, remember, is for a gamma ray, this is enormous, right? That is enormous. So if I'm going to say that this is a gamma process, and then if I look at the X-ray, right? This is the energy for the X-ray. So remember, when I look at the X-rays, it's about 1,000,000 times smaller. So now what happens? These guys jump. As they jump, they're going from high to low energy. And so when you go to look at how much energy is released, you could see that there's a big difference. So when I compare these two, this guy, again, so if I look at the energy of this guy is going to be about 10 million electron volts. And this guy right here is going to be around 10,000 electron volts. Radically different. So then this here is the energy emitted by the gamma ray. And this is the energy emitted by the X-ray. And what you're seeing here is that this is telling you is that the energy of the gamma is greater than the energy of the X-ray by a lot. So that's where X-rays come from. So now, how do you generally do that? So what you're seeing here is X-rays originate from the electrons in the atom, right? So an X-ray originates from the jumping electrons to the lowest energy level. And as a consequence, this causes excess energy to be released. So how do you typically do this? So what you typically do is that you have how do I do this? So I didn't plan to do this, but let me just try to think about this. So typically what happens is that you have a hot filament. Okay, this is a hot filament. And what they say here is that by heating up this hot filament, you then produce, they say that you boil electrons off. And let me tell you, that is actually pretty close to a good way of looking at it. So now these electrons are accelerated. And what you do here is that from here to here, you put a very high voltage. So this is a high voltage. And if you're in the know, this voltage is of the order of kilovolts. And look at the number. Look at that. Less than 10,000 is X-rays. Look at that kilovolt source. So then what you do here is that when you shoot this, you then they typically have it something like this here. They put an angle to this. And then what they do here is they put a piece of metal right here. So in my case, I would say that this metal here could be copper, but the ones that people typically talk about is tungsten. But tungsten's a little bit harder to talk about. And so as these electrons do what? They knock off one of these inner electrons, and then an electron from a higher energy level drops to a lower energy level. And as a consequence, what do? They emit the X-rays. And that's how you typically get X-rays. So here, I'm going to talk about multiple ones simultaneously. So now, here I go. So what I'm going to do here is that I'm going to have three. So I'm going to talk simultaneously about UV, visible, infrared, microwave, and finally, radio waves. So they're all connected to the same process. So these are produced by energy shifts of electrons whose jumps are not as large. So when you look at the energy, it turns out that UV is higher energy than visible, infrared, microwaves, and radio. So then in this end here, this guy right here is going to be the high end, the relative high end for these, and this is going to be the lower. So the higher the jump, the closer you're at UV lights. The lower the jump, the closer you are to infrared here. So this is all relative here. So now here's an image that I think is a really good image. And I think I'm going to make this a little bit bigger so it's easier to see here. And what you're seeing here is that this is only for hydrogen. Okay, so this is the hydrogen. This is the hydrogen atom. And it also goes through all of these other atoms too, but hydrogen's the easiest, and that's what I'm looking at. So what you see in hydrogen is you get a class of jumps. The bigger the jump, you get something called Lyman, and they produce ultraviolet light. Look at the purples. These jumps are bigger. Now, if you want to get to visible light, this is the Balmer series, and the Balmer jumps are smaller than the Lyman. So you could see here is that right here, you could see that, look at this. This right here is ultraviolet. It has a bigger jump. If you look over here, look at Balmer. It has the second biggest jump. And then what you're seeing in hydrogen is that you're starting to see, look at that, infrared, infrared, infrared. So there's a bigger spread in infrared, but there's less. So what you're seeing here is it says something like this here. So if I have a Lyman jump, then that means that it's larger. And if it's larger, it has more energy. You know what? I'm going to run out of space. So I'm going to pull this down here. So if I have a Lyman jump, it has a larger jump. So therefore, it has more energy. And as a consequence, it has a higher frequency. So when I say this, I'm really saying that this is all relative to UV, visible, infrared, microwave, and radio. Obviously, the gamma and the X-rays have much, much bigger jumps. But then if you look at the next series, look at Balmer. Balmer doesn't have as big as jump as Lyman. So then if I look at Balmer, a Balmer jump has it's a, I don't know, mid-size. So therefore, it has mid-energy, and therefore it has a mid-frequency. But if you go to like these others, right, I'll just mention one of them. How about Passion? Jump. I could have picked bracket, but it's the same thing here. And then you could see here is that this is a smaller jump. So therefore, this has low energy, and as a consequence, it has a low frequency. So that's, by the way, I could do this with microwaves and I can do this with infrared. But now what I want to do here is that let's talk about each of these individually, because there's so much interesting stuff. Okay, there's a lot of stuff here. So let's talk about UV light. Okay, so when I look at UV light, what am I actually seeing here? I would say that most UV comes from the sun. That's not a surprise, right? We wear sunscreen and there's A and B, long or short UV, and that tells us a lot. But on Earth, UV is primarily produced by light bulbs. So what do I mean by light bulbs? Well, I mean, one common source of UV light, so a common source of UV light are tanning booths. They produce UV light so that you can artificially get tanned. Now, what's really interesting about this, UV light is absorbed by regular glass, while quartz glass allows it to pass through. So what's interesting about that is that if you're driving your car and you have glass, of course, that glass absorbs all the UV light. That doesn't mean that you can't get burned, because you do generate heat inside. Okay, let's go to the next one. Let's talk about visible light. Well, visible light, man, there's so much this. Maybe we should start labeling these, because there's a lot. So the first thing that I want to do here is I want to look at the visible spectrum of the sun. So let's go look at that. Now, I don't want to spend too much time on it, but there's so much to unpack here. Look at that. Here's the visible spectrum of the sun. Okay, and these numbers are important, okay, because there's some sloppy numbers that people talk about, but they're talking about the light at the top of the atmosphere. We don't want to talk about the light of the top of the atmosphere. We want to talk about the sun. So here's what you're seeing here. So the first thing, so let's order them. Let's go over here. So the first thing that we should look at is that the temperature of the sun is around 5,800 degrees Celsius. Okay, that's the surface of the temperature. So when you look at this curve, this is the black body curve for the sun. If you look at that, this tells us here that the peak intensity is in the visible region. And it looks like it's around 500. So I would say that this right here is the peak right here, right? That looks like that's the peak. It looks like it's around 500. It turns out that it's slightly below. So the peak intensity is in the visible region at 487 nanometers. So what does this mean? It says here that, so if I look at visible light from the sun, visible light is 44% is visible light. 40, so if you look at the next one, the sun produces more infrared than visible, and this is at 49%. And it turns out that if you look at UV, only 7% is produced in UV. The rest of this, so if you look at all the other ones, right? X-rays, gamma rays, and radio waves. So then X-rays, no, let me do it right. So gammas, X-rays, and radio waves, this produces, it produces actually less than 1%. So let's say 1%. So most of the light is infrared, right? So this tells you here is that this is the most light emitted. So that tells you how the breakdown of the light is. But let's look at some of these other things here. There's some misconceptions that I think we should definitely look at. So one of them is that, let's talk about, I called that 2, so how about 3 here? There's a misconception about the color of the sun. So the question that we should ask here is, what is the color of the sun? The misconception is that it's yellow or orange or even red. So what we should do here is that we should define what we mean by color here. So here's a good definition that you should have. Any object that emits, and this is crucial, all frequencies of the visible spectrum is white. This has nothing to do with the sun. Any object that emits all frequencies of the visible spectrum is white. Look at the spectrum of the sun. You could see violet all the way to red are produced in equal amounts. So in this case, the sun is white, not yellow. On a clear day, look at this damn sun. You'll see that it's white. It's not yellow. And the reason why it's sometimes perceived as yellow, orange, or red is because of the atmosphere. The atmosphere, so let's be a little bit more careful here. So the conditions of the atmosphere change the color appearance of the sun. That's why at sunset you could see a red sun. Does that mean that the sun is red? Of course it's not. So then the question is, what is the color of the sun? So what is the color of the sun? Now, we already said that it was white. Of course it's white, because look at the spectrum. You could see that there's equal amounts of light emitted. But if you were to put a color on this, look what you're seeing right here. At the peak, this is really a green, blue sun. It emits most light in the blue and green sun. So if you ask me, if I was forced to say what is really the color, I would say that since 487 nanometers is the most light emitted by the sun, it's closest to a blue-green color. So if you look at this thing, you could probably say, like, that's the color of the sun, or pretty damn close. That's a NASA picture. So yeah, if you're going to force me to give you a color, that's what I'm going to do. But for all intents and purposes, you look at the spectrum and you can see here that it's not even close to yellow. Yeah, I'm not going to get into any debate with anybody, but again, the appearance depends on the conditions, so I'm not going to go there. So now let's keep looking at this guy right here. So before we get into more details of the visible spectrum, one of the things that we should probably talk about, there's a lot of strange things in the color. Go back and you look at the spectrum. Look at the spectrum right here. Look how many different types of spectrum there is. Right? In this picture, look at the little sliver of visible light. It is super thin. Right? Maybe I should take this picture down with me, and let's go look at this all the way down here. So maybe the question that we should answer now, since we've already gone along this direction, the percentage of visible light relative to the whole electromagnetic spectrum is tiny. I mean, is tiny, tiny, tiny. We only see 0.0035% of the electromagnetic spectrum. Humans are so colorblind to what's really out there. The entire rainbow that we observe by the human eye only makes 0.0035% of the electromagnetic spectrum. Think about that. That is tiny, super, super tiny. And color becomes really, really awkward. Okay, it becomes really, really, really awkward. So what number is that? Let me go back here. That's 3. Let's go to 4. Color is a human perception. Nature does not see color, which is really, really hard for a lot of people to accept. Unfortunately, that's not my problem. That's yours. Color is a human perception. We don't care about color. We care about energy. Now, here we see the word photon. Photon is the quantum mechanical description of light, which I don't want to go there. So when you're looking at this spectrum, remember, energy is the way we should be looking at light. That's not what happens. So the common way to describe visible light is wavelength. You're going to see that describing light as wavelength becomes a major problem. So here we go. So if we look at the shortest wavelength, and this is violet, okay, this is violet, the range of wavelength for visible light goes from 380 to 750 nanometers, where this is red. So to show you that color is a human perception, let's talk about some colors here. So in optics, violet is a spectral color. That what that means here is that this refers to a single wavelength of light. Purple is a color of various combinations of red and blue. So what we're seeing here is that some people will say that's purple, but that's a human perception. That's not the same as violet. They're not the same thing. They're actually two different colors. So I mean, that's one of the things about colors here. But when we talk about this, we're really looking at what is the spectral one to actually do this. So let's look at the other one. So then there's infrared waves. So if I look at IR waves, these are typically, we saw that it depends on the jump of the electrons in the electronic structure. But how do we typically do this? So these are typically generated by vibrations / rotations of molecules. And a lot of the times, these are also called heat waves. So remember, all of these refer to jumps, electron jumps in the structure. Right? And sometimes you'll hear people call it thermal radiation. And any object that has a temperature radiates infrared waves. So any object that radiates heat emits infrared waves. There's lots of ways to look at this thing. Here, I just picked, I have a picture that I got offline that looks something like this. So what you have here is in the red, this guy right here in the red, this guy contains hot water. This one contains cold water. And down below is an image that shows the emission of infrared. So you could see that the hot water, you can clearly see the glow on the one to the left, but in the dark, colder water, you could see that it's emitting a different amount of infrared radiation. So we only have two more, but these are quite interesting as well. I'm trying to limit here. Let's talk about microwaves. So when we talk about microwaves, this is typically what happens here when you look at microwaves. Microwaves are the portion of the band found at the higher end of the radio frequency spectrum. So these are, this is the band at the higher frequency end of the radio spectrum. And a lot of times they distinguish radio waves from microwaves, not because they're not the same process, but they're technologies that they use. Radio wave technologies is different than microwave technologies, but microwaves are still the same type of thing. I mean, God, we could go on forever here. Maybe I should wait. Like, microwaves are not reflected by the ionosphere. That's important because radio waves can travel around the world because they bounce off this ionosphere, and as a consequence, you could send radio messages quite far. Microwaves travel in straight lines instead. And if you are not in the straight line of travel, man, the microwaves are going to dissipate. So it's important that it's straight line. But here's some interesting facts on microwaves. I love these microwave facts. I think they're fun. So the first thing that we should think about is that the microwaves, I should be careful. Microwaves were discovered by accident, right? It's discovered by accident in the I believe it's the 1940s, maybe the 1950s. And the reason why I think this was really interesting, there's a guy named Percy Spencer, and he was working on radar, especially with magnetrons. And so he had a candy bar in his pocket, and he noticed as he was working with these microwaves that it melted the candy bar in his pocket. Being a great physicist, what did he do? He actually spent the time to look into it and figured out that there was this thing called microwaves. Okay. Now, another thing that I find really interesting here, is that the first microwaved food was popcorn. And let me tell you but in fact, I think the first day he did it with popcorn. And if I remember correctly, the second day he did an egg. He microwaved an egg in his microwave oven, and no surprise, the egg exploded everywhere, which was, I'm sure it was quite humorous at the time, or quite scary. I don't know. The other thing that I think is really interesting is that the first commercial microwave was called the radar range. Look at that name, radar range. I love that name for the microwave. Too bad it didn't stick here. But check out this microwave oven. Oh, this is a beauty. Look at this guy right here. Look at this microwave. So this microwave, I think this was put out in the 1950s. Look at this. This is 6 feet tall, and it was some awful number. I can't remember. It's somewhere between 700 to 800 pounds. Wow, that's pretty impressive, wasn't it? I think that it sold for $5,000 in 1950. By the way, if you do this for inflation, I looked this up. Inflation today, by today's standards, that would have cost $52,600 today. Wow, that would have been really expensive, obviously. And today's ones are way more powerful. So the last one that I'll talk about, and I'm going to try to limit this discussion here, I want to talk about radio waves. Again, I'm not doing any justice here. So a lot of radio waves, can I say? God, there's so much. Radio waves, we typically think of them as electrons being accelerated by antennas. So what do I know about the radio waves? They have the longest wavelengths in the electromagnetic spectrum. And the range their range is huge. They go roughly, they go roughly to a size of a football. Okay. Right. They essentially go from a football length. And if this is the radio wavelength, to the size of planets. That's what I remember. To the size of planets. That is a huge, huge range. In fact, the discoverer of wireless transmission was done by Hertz, where he sent radio waves from one location to another. So what do we know about radio waves? Typically, radio waves, there's a range, and you can actually see that if you had one of these old school antennas. There's low frequency, medium frequency, high frequency, and very high frequency. So since I'm older, I remember these antennas here. So when you look at, so what are the benefits? So the benefits of radio waves is that one can use them for communication, and radio. Turn on the radio. And the reason why this here is that radio waves are transmitted easily through the air. Furthermore, they do not cause damage if absorbed by the human body. That makes them ideal. One of the things that I was saying earlier is that radio waves, when you look at them as communication, they can travel long, long distances. And the reason why is that you can reflect them off of clouds as well as layers of the ionosphere. And so you can get them to relay between satellites. And that makes them really useful.